Hello everyone and welcome back to Networks class. Last time in class we discussed max flow interdiction at the beginning of class, and in that discussion we were able to pull out the general rules to create an interdiction model for essentially any network problem that you might have. And then for the rest of class we discussed min-cost flows. So we got some basic intuition about this problem, like the fact that min-cost flows are driven by essentially one of three things: either a supply demand, a lower bound, or a negative cost that we want to take advantage of. And the plan for today is to do a couple of application of min-cost flows. So first, we're going to do this application of production and transport planning, where we pretend that we're a large company and we just want to plan how much of the various products we should produce to be able to maximize our profits. And then towards the end of class, we're just going to do a small application on how we can track multiple moving objects with successive frames in a video camera. So let's just begin with this first application, which is production and transport planning. So the idea behind this application is that we're going to pretend that we're operating, let's say, a large car manufacturing company. So and let's say that our company has two production plants, one in Mexico and one in Canada. So we have two plants, one in Mexico, one in Canada. And suppose that we produce three types of car models. So what I mean by this is, for example, we produce Pontiacs, let's say, and we produce Mercurys, and let's say that we also produce Hummers. And we can produce each of these three models in any of our two plants. So in addition to the models in the plants, we have two retail centers. Let's say we have a East Coast retail center and a West Coast one. And each retail center has its own demand for each type of vehicle. So what I mean by this is that maybe Pontiacs are very popular in the East Coast, but maybe not so popular in the West Coast. So we have different demands for each of these models in each of the retail centers. And the basic question that we have to answer with our model is, how many cars of each type do we produce at our plants? Where do we ship those cars? To maximize profit of the company. So that's the basic question, and we're going to answer this question using a minimum cost flow model. So let's just begin to brainstorm what this model might look like. So in particular, we have to account for the fact that we have these two different plants the fact that these plants produce these three types of models, and the fact that we have these different retail centers east and west. So let's just begin here by saying that we have these two different plants. So one in Mexico and one in Canada. So we're going to create a Mexico node and a Canada node that correspond to these two plants. And in Mexico, we can produce Pontiacs. And we could produce Mercuries as well. And we could produce Hummers in Mexico as well. So we're going to model that by having these three nodes that correspond to Mexico Pontiacs, Mexico Mercuries, and Mexico Hummers. And we're going to have a similar thing for Canada. So Canada Pontiacs, Canada Mercuries, and Canada Hummers. So this just kind of gets us started on some of the nodes. We know over on this side, eventually we're going to want to sell these cars. So we're going to have an East Coast and a West Coast node that represent our two distribution centers. But let's worry about the sales part of the graph in just a minute. Let's continue working on the production side of the graph here. So these cars that we're going to be producing in Mexico and Canada, they have to come from somewhere. So let's create kind of a fake start node S where all of these cars are going to come from. So these cars are going to just get created at this fake start node S, come up into this Mexico node, and then the plant in Mexico can produce either Pontiacs, Mercuries, or Hummers. Now, if we're modeling this with min-cost flow, each of these edges has four things associated with it. So it has three pieces of data and one decision variable. So the three pieces of data with each of these edges is a cost, a lower bound, and an upper bound. And the one decision variable that's associated with the edge is a Yij that tells me the flow of material across this edge. So similarly, this edge right here has the same four things associated with it. It has a cost, a lower bound, and an upper bound. And it also has a decision variable that's going to be the flow across the edge. So let's figure out what each of these things mean in terms of this application of production planning. So the main difference between flow on this edge from S to Mexico and on the flow from Mexico to Mexico Pontiac is the fact that on this first edge we're not differentiating the type of car that is going across the edge. So this decision variable Yij is the total number of cars produced in Mexico, regardless of the type of the car, while this variable here on the flow from Mexico to Mexico Pontiac is the number of Pontiacs produced in Mexico. So it's on these three edges that we're beginning to differentiate a Pontiac is different from a Mercury, is different from a Hummer, while in this original edge, everything is grouped together. And so quite similarly to the difference in these decision variables, we have a similar distinction in what the cost, the lower bounds, and the upper bounds mean. So this cost right here is a model independent cost of producing a vehicle, producing a car in Mexico. So we're going to have to pay this cost, and it's the same cost regardless of whether we're producing a Pontiac, a Mercury, or a Hummer. So you can think of this as maybe some administrative costs or some basic raw materials that every type of car requires, regardless of what kind of model comes out at the other end. This cost right here that goes on the arc from Mexico to Mexico Pontiac is a Pontiac-specific cost. So in other words, the cost across this edge is only going to be experienced by the Pontiacs we produce in Mexico. So if we're producing a Mercury, we can have totally different costs here than if we're producing a Pontiac. And quite similarly, we could have completely different costs for producing a Pontiac in Canada than for producing a Pontiac in Mexico. So that's why we have separate edges here with separate pieces of data. So similar to the breakdown of the costs here in terms of a model-independent cost and a model-specific cost, these upper bounds have similar interpretations. So the upper bound on this first edge from S to Mexico is the total production capacity in Mexico. So that means that that's the production capacity for the total number of cars that we make, regardless of which type of car it is. While this upper bound right here is the maximum number of Pontiacs we can produce in Mexico. So this is kind of a Pontiac-specific production capacity, while on this first edge is the model-independent production capacity. So now we have some interpretations for these costs and these upper bounds. And so let's similarly get an interpretation for the lower bounds here. So the lower bound on this edge from S to Mexico, that is going to force us to produce at least so many cars in Mexico. So you can think of this as kind of a contract on the minimum number of cars we have to produce in Mexico. On the other hand, the lower bound on this arc from Mexico to Mexico Pontiac, that is the minimum number of Pontiacs to produce in Mexico. So again, just the major difference between this edge and this edge is the fact that this is model independent and this is dependent on the specific model. Okay, so now we have a reasonable interpretation of the production side of this graph. So cars get created at S, and we choose to either create them in the Mexico or Canada plant. They experience some model-independent costs, upper and lower bounds, and then we have some model-dependent costs, upper and lower bounds. So let's spend a little bit more time thinking about the distribution side of this graph. On the distribution side so far, we've just created these two nodes for the East and West Coast retailers. But similarly to the way that we broke out Pontiacs, Mercuries, and Hummers that we produced in Mexico, we have to break out these different models for each of these retailers. So we're going to have East Coast Pontiacs, East Coast Mercuries, and East Coast Hummers. West Coast Pontiacs, West Coast Mercuries, and West Coast Hummers. So the reason that we broke these out is because we might have different kinds of demands for each model in the East Coast. So we might want to sell 100 Pontiacs, but we might want to sell only 50 Mercuries. And so that's why we need sort of different edges to put those constraints on here. So now let's think about how we can connect the production side to the sales side. So Pontiacs are getting created in either Mexico or Canada. And we can sell them either on the West Coast or on the East Coast. So the way that we're going to represent this is with edges that kind of look like this. So what these edges are representing is transportation. So they have a cost, a lower and an upper. And the cost here is the per Pontiac cost of transporting from Mexico to the East Coast retailer. The upper bound here is kind of our total transportation capacity for moving Pontiacs from Mexico to the East Coast. So total transportation capacity for moving Pontiacs from Mexico to the East Coast. And the lower bound right there would be some kind of contract with the trucking company that guarantees that we'll provide that trucking company a certain amount of business. So this is a minimum number of Pontiacs we have to ship. Again, and it's the minimum number of Pontiacs we have to ship from Mexico to the East Coast because that's where this edge is going. Okay, so these edges from the production side to the sales side kind of represent transportation from our plants to our retail outlets. So now let's think about the data on the edges right here. So from West Coast Hummers to this West Coast retailer. So this has a cost, a lower bound, and an upper bound. So this cost right here could represent, so could be negative, representing the profit of selling a Hummer on the West Coast. So this is where we actually make money by selling Hummers on the West Coast. And of course, we could have different prices on the West Coast versus the East Coast because we have different edges here, and different prices for selling a Hummer versus selling a Mercury versus selling a Pontiac. These upper bounds right here tell me the maximum number of Hummers I could sell on the West Coast. So you can think about this as measuring the demand for Hummers on the West Coast. The reason for this is that if this number is 100, it just tells me I can sell 100 Hummers maximum on the West Coast. And of course, I could have some kind of lower bound that forces me to sell a number of Hummers on the West Coast, even though they might be losing me money. So this is a requirement to sell some number of Hummers on the West Coast. So that's what the edges here from the different model types to the retail centers represent. They represent kind of the sale of that particular model. So obviously the cars that get sold, they have to kind of go somewhere in terms of our flow model. So let's add an end node T, and then let's add edges from each of these retail outlets to T. And these edges, of course, are going to have a cost, a lower bound, and an upper bound. So let's think about what their costs, lower bounds, and upper bounds mean. So at this point, we've combined all of the three different model types. So across this edge, we cannot differentiate anymore Pontiac from a Mercury from a Hummer. So this cost right here is a model-independent cost of selling a car on the West Coast. So regardless of what type of car we sell, it might cost us some amount of money to pay the salespeople, and so or some kind of administrative costs, and so those costs would go on this edge right here. The upper bound on this edge, this upper bound kind of tells me the maximum of the total number of cars I can sell on the West Coast. So maximum number of cars we can sell on the West Coast. So this is a maximum number regardless of type. So you can think about it as perhaps a lot size for our retailer. So our lot can only hold 1,000 cars, and so we can only sell 1,000 cars total regardless of what type those 1,000 cars happen to be. So that's what the upper bound is. And the lower bound here has similar interpretations as the lower bounds elsewhere in this model, which is, you can think of it as a contract that we have to satisfy. So we have to ensure that we're selling at least this lower bound of cars on the West Coast, regardless of what type of car it is. So minimum number of cars to sell on the West Coast. So let's just discuss all of these costs a little bit more. So think about the costs on the production side. So here I have a cost that's independent of the type of car. And here I have a cost that's dependent on the type of car. One of the things I could do is I could just make the model independent cost be 0 and add those costs into here, into these arcs. Because any Pontiac that's getting created is going to first experience the cost here, and then to that is going to be added the cost across this arc. And so as long as it adds up to the right thing, I could move all of the costs so that they are experienced on this arc right here. But one thing that I cannot do is move the upper bounds in this way, the same way that we're moving these costs around. So the upper bound on this edge is the total bound on the number of cars produced in Mexico. And so that's bounding the sum of Pontiacs, Mercurys, and Hummers, while the bound right here is only bounding Pontiacs produced in Mexico. So a similar thing is going here on the sales side. So this upper bound U is a bound on the total number of cars, while the upper bound on just one of these edges, like this Hummer edge, is just the specific bound on the number of Hummers that we can sell in the West Coast. Okay, so now we have sort of a fully structured graph. So let's imagine that we're very careful about finding the exact right cost, lower and upper bounds to put on all of these edges. So we're very careful with that. We put it into CSV files, we put it into GAMS, and we ask GAMS to figure out how many cars should we be producing in Mexico, Canada of each type, how should we be shipping it to our retail centers, where should we be selling these to maximize the company's profits. If you do it for this graph as it is, the answer that you'll get out is either 0 or infeasible. And that's because there's nowhere for these cars to be coming from. So the node balance constraints are going to force us to not have any flow on these edges. So to really make this a complete min-cost flow model, we have to add this backwards edge from T to S. And the only reason this edge exists is to kind of make the node balance constraints on S and T match up correctly. So now any car that we produce in S is going to go through here, experience some kind of costs for production, some profits for getting sold, and then at T it's going to go back to S and everything is going to balance out. So this edge that we added, its only purpose is modeling, and so its cost is going to be 0, its lower bound is going to be 0, and its upper bound is going to be infinity. So it's just there to make sure that all the node balance constraints match up. So let's discuss about why we should put this backwards edge as opposed to putting a supply and demand. So imagine putting a supply of 200 at S and a demand of 200 at T. If we did that instead of putting this backwards edge, then what we're doing is we're forcing the model to create exactly 200 cars. So here we're saying create exactly 200 cars, and yeah, figure out the way that those 200 cars are going to make me the most profit. But we're not letting the model itself figure out how many cars should be created. While with this backwards edge from T to S, the model itself figures out the number of cars that we should be making to maximize this company's profits. Now, if we take this min-cost flow model, we stick it into GAMS, and we run our program, and we get out a positive number, that means that the company is losing money, that we have contracts in terms of lower bounds, and to satisfy those contracts, we have to spend more money than we make at actually selling these cars. If we get a negative number, that means that the company is making profit. So suppose that this route right here makes us a profit. So from S to Mexico, Pontiac to the East Coast. So in other words, if I make Pontiacs in Mexico, move them to the East Coast and sell them over there, the company makes money. So if we're making money across this path, and we're trying to maximize the profit of the company, naturally we're going to try to make as many Pontiacs as possible along this route. But the thing that is going to stop us from saying that we're going to create an infinite number of Pontiacs is several things. So one thing that might stop us is our production capacity here, because our plant can only produce so many Pontiacs. Another thing that might stop us is the demands, so the upper bounds on these edges, which tell us how many Pontiacs we could sell on the East Coast. So just because there's a route that makes money doesn't mean that the company is going to make an infinite amount of money out of this model. So that's the basic idea for our production planning model. But let's discuss just a couple of small twists to this model. In particular, let's have the first twist be the following. So suppose that I have kind of a graduated demand scale for Pontiacs. So let's say that the first 1,000 Pontiacs, there's a lot of customers out there that are really excited about Pontiacs. So these first 1,000 Pontiacs we can sell, let's say, for $200,000. But after we sell those first 1,000, the next, let's say 5,000 Pontiacs, after that, we've sort of gotten our most excited customers to buy Pontiacs, and then we can't sell these next 5,000 at $200,000. Maybe we can only sell them at $150,000. After that, let's say the next 10,000 Pontiacs, their price really bottoms out because we flooded the market. And let's say those we can only sell for $5,000. So how can we incorporate this graduated scale in terms of the prices of Pontiacs in our model? The way to do this is the following. Let's just focus in on this area of the model right here, the one that connects the East Coast Pontiacs to the East Coast retailer. So currently we have just a single edge that connects these two nodes. And it has some cost, lower bound, and upper bound. So let's do this. Let's make the cost be minus 200,000. The lower bound be 0. And the upper bound be 1,000. So this says that the first 1,000 vehicles we can sell for $200,000 a piece. Then let's add another edge. And this edge is going to have a cost of minus 150,000. That represents the profit of 150,000. It's going to have a lower bound of 0 and an upper bound of 5,000. So this represents that we can sell 5,000 vehicles at $150,000 a piece. And then we'll have a final edge here that has a cost of 5,000, lower bound of 0, and upper bound of 10,000. And this is the last part of our graduated pricing over here. So let's think about the very first Pontiac that moves through the system. We're trying to, or the model is trying to minimize cost. So the very first Pontiac here is going to take this bottom edge because that's the edge that gives it the minimum cost. And in fact, as long as we have less than 1,000 Pontiacs, we'll always be taking this bottom edge. But as soon as we have 1,001 Pontiacs, this upper bound is going to kick in. And so we can only send 1,000 Pontiacs down the bottom edge. And the 1,001st Pontiac will be forced to take this next best edge right here. So the 1,001st Pontiac is going to sell for 150,000 instead of 200,000. And kind of a similar thing after that. Our 6,001st Pontiac will be forced to take this third edge, which means we'll be selling it for $5,000 instead of 150,000. So one last comment about this small twist on our problem, which is that if you try to program this in GAMS, GAMS doesn't accept multigraphs. So we can't have these three edges all going between these two nodes. And so what you'd have to do is introduce some kind of fake nodes in between here. And as long as you have these fake nodes, everything will work out. So for example, you could put these costs, lower bounds and upper bounds, just on one side, and have the other edge on the other side be totally unrestrictive. And we'd get the same kind of behavior as in the multigraph that we wanted. Okay, so that's the first twist to this problem. In the next twist of the problem, suppose that I have some kind of future information. So I know that the price of Pontiacs on the East Coast is going to increase, or the demand is going to increase, and I want to plan my production ahead of time. So in other words, in year 1, I might want to produce some extra Pontiacs and store these Pontiacs from year 1 to year 2 to year 3, and then sell them in year 3 to kind of build up my inventory and sell it when the price is high. So let's think about how we can incorporate something like that in our model right here. The basic idea of that is to do time layering of the graph that we have. So let's just focus on this part of the graph right here to think about how we can do this time layering and planning for future years. So what we're going to do is create a Mexico year 1 node, Mexico year 2, Mexico year 3. And S is going to be connected to each of these. And then we're going to have Mexico Pontiac's year 1, Mexico Pontiac's year 2, Mexico Pontiac's year 3. So that's going to represent producing Pontiacs in year 1, producing Pontiacs in year 2 and year 3. But now in addition to shipping these out, so I could potentially ship these out to East Coast Pontiac's year 1, East Coast Pontiac's year 2, East Coast Pontiac's year 3. So a Pontiac that gets produced in year 1, I could ship it out for sale in year 1, or I could potentially store it for the next year. A Pontiac that gets produced in year 2, I could ship it out for sale in year 2, or I could store it for the following year, for year 3. And then in year 3, we could also ship things out. And we're not modeling later years, so we're going to say in year 3, we ship everything out. So let's think about the new sort of paths that we've introduced in this graph. So previously, for year 3, the only thing that we could do is produce a Pontiac in year 3 and then ship it for sale in year 3. But now we can sell Pontiacs in year 3 in a different way. So we could produce them in year 1, store them from year 1 to year 2, store them again from year 2 to year 3, and then ship them out for sale in year 3. So we have these new edges that are kind of crossing across our time layers. So let's think about what these edges mean. So there's a cost, a lower bound, and an upper bound on each of these. So the cost here is going to be something like the storage cost. It's how much does it cost me to store a Pontiac from year 1 to year 2. The upper bound is going to be the maximum storage capacity. So it's the maximum number of Pontiacs we can store from year 1 to year 2. And kind of a similar thing for this next edge. We're going to have a storage cost from year 2 to year 3, and the maximum storage capacity from year 2 to year 3. So now a Pontiac that we produce in year 1 and store to year 3 is going to experience these costs. It's going to experience a production cost in year 1, a storage cost from year 1 to year 2, a storage cost from year 2 to year 3, and then transportation cost in year 3, and then the sale in year 3. So you could do a similar kinds of vertical storage at the actual point of sale, so at our retail center. And then that will let you take advantage of changing transportation costs, because maybe it's cheaper to transport the Pontiac in year 1 versus year 3. So that's another kind of twist on the basic model we can do, is just introduce time layering and let ourselves do this planning for more than just 1 year at a time. But some of the basic rules of thumb to pull out of this model are the following. The first rule of thumb is to just pull out this concept of tracking a different type of vehicle. So here we weren't tracking which type of vehicle it is, but here we've differentiated the types, and we're keeping them differentiated throughout. So if at any point I mix Pontiacs and Mercurys, I will no longer be able to tell which car is a Pontiac and which car is a Mercury after that. So we kept these cars separate until it no longer mattered, and then we can combine them and sort of account for the end of the graph right here. The second important thing to pull out is this backwards edge. So the backwards edge from t to s, what that let us do was let the optimization problem decide how many cars should get produced instead of us ahead of time deciding on the number of cars that get produced. And there's lots and lots of twists you can go with this problem. So once we have this basic min-cost flow problem, you can start adding integer variables on top of that sort of account for interdictions of this process. They could count for capacity expansion in terms of where to build new factories, how much new factories to build, where should I close down factories, etc., etc. But that's the basic production planning and transportation model. So now let's talk about our second application for today, which is just the application of tracking moving objects. In this application, we have a video camera that's sort of in quick succession taking frames. So each of these frames looks like an image. So imagine that this is frame 1. So in frame 1, let's say we have 3 objects. And in frame 2, we have these same objects, but they've moved a little bit. And I want to be able to track these objects from one frame to another. So to do this, let's think about overlaying these 2 frames on top of each other. So these are the objects as they appeared in frame 1, and on top of that, I'm going to just put the objects in frame 2. And so there's some distance here between the objects in frame 1 and the objects in frame 2. And we want to be able to do this tracking to kind of figure out where each object moved. And we're going to do this with a minimum cost flow model. So to do this, imagine creating the following graph. So here we have the frame 1 objects and the frame 2 objects. So here are these 3 objects from frame 1 and the 3 objects from frame 2. And we want to figure out where to match these frame 1 objects. So this object from frame 1, it could have been this one in frame 2, it could have been this one, or it could have been this one. So same thing for these other 2. It could have been this one, could have been this one, could have been that one, etc. So if we're going to do this with minimum cost flow, and we want the best match, let's think about what the cost lower and upper bounds on this edge would mean. So you can think of the cost here as a similarity measure. And the similarity measure is kind of more negative the more similar these objects are. Similarity could be determined by a lot of things. So it could be determined by the distance of the 2 objects, one from another. They could be determined by whether the 2 objects have the same color, whether they have the same shape, any kinds of features that we can pull out of the image here. But the important part is that we need the similarity measure to be more negative the more similar these objects are. And that's because we're going to determine the minimum cost flow. And so we want more negative numbers to be better. So now we want to make sure that each one of these 3 objects in frame 1 gets matched to exactly one object in frame 2. So to make sure that the objects in frame 1 get matched to exactly one object in frame 2, we want to make sure that there's flow on only one of these arcs. And the flow on the arc is going to tell us where that object got matched. So to do this, we're just going to put a supply of 1 on each of the frame 1 objects. And we're also going to put a demand of exactly 1 on each of the frame 2 objects. So what this does is it makes sure that exactly 1 unit of supply leaves here, and exactly 1 unit of material arrives at each of the frame 2 objects. So in other words, I can't match both the top frame 1 object and the second frame 1 object to this second frame 2 object. It'll be a one-to-one matching of frame 1 objects to frame 2 objects. And this matching is going to be done in such a way as to find the greatest similarity across all 3 matches. So that's going to allow us to track the objects from one frame to another. But the important thing about this application, besides this concept of how to get an exact one-to-one matching from frame 1 objects to frame 2 objects, is the fact that we can do this in several different ways using min-cost flow. So I've shown you one way up here. So we figured out what the costs are. These lower bounds, we're going to have them be 0 because we might have no flow on the object. And the upper bounds here, it turns out that they don't matter very much. So they can be anything bigger than 1. So as long as I can send 1 unit across this edge, I'm happy. So I can make these upper bounds be 1. I can make them be infinity. Either is fine. So let's think about a different graph for being able to do the same matching. So here's another way of doing it. So again, we have the frame 1 and frame 2 objects. Again, we have the similarities. And then an upper bound of, say, 1. But what we'll do is introduce 2 nodes S and T to connect to either side of this graph. And we'll give a supply of 3 at S and a demand of 3 at T. And on this edge, what we'll do is we'll put a cost of 0, a lower bound of 0, and an upper bound of 1. So same thing over here, 0, 0, 1. And same thing over here, 0, 0, 1. And 0, 0, 1. So let's see what this is doing. It's saying I have to move these 3 units from S to T. But because of these upper bounds, I can only move 1 unit out of each of these arcs. So since I can move only 1 unit out of each of these arcs, that means only 1 unit is going to show up at each of the frame 1 objects, which means each of those objects can only have one of the edges going out of it, have flow on it. And similarly, these upper bounds make sure that we don't have 2 frame 1 objects matched to a single frame 2 object. So that's our second method that we can do this matching between the frame 1 and frame 2 objects. And here's a third method that's just as good, equivalent to our first 2 ideas. So again, we're going to have the similarities and the upper bounds of 1 between the different objects. We're going to again have S and T. But on these edges, let me have a cost of 0, a lower bound of 1, and upper bound of 1. So same thing over here, cost of 0, lower bound of 1, and upper bound of 1. And now, instead of adding these supplies and demands of 3 and 3, I'm going to have this backwards edge with a cost of 0, lower bound of 0, and upper bound of infinity. So now, because of these lower and upper bounds, I'm making sure that there's exactly 1 unit of flow across each of these edges. And this backwards edge makes sure that the flow balance constraints at S and T are met. So it kind of substitutes for the supply and demand imbalance at S and T in our previous example. So this application should demonstrate to you that whenever we have a min-cost flow problem, there's often multiple graphs that solve that problem. So, and these are really equivalent. And this is very formally, you can show this because it's possible to come up with a set of rules that transform one of these graphs to another. So we won't talk about this in detail in class, but these things are exactly equivalent if you just think about some rules in terms of algebraic manipulation. But in terms of the graphs, it also makes sense why they're equivalent from an intuitive point of view. So that completes lecture for today. Thanks a lot for listening. See you all next time.